scientist who speaks the price of Yale blinded meetings.
All right. Welcome back, guys. You can totally watch the video on your own if you like. I like playing it usually when we're in person, but since we're online, you can play it if you want to. If you're a fan of the 80s, yay, I'm a child of the 80s. If you're not, I'm sorry for my young people in the class. So I'll have some more modern music as we move along through the class. So we are back on chapter 2. This video is going to go over chapter 2 in your book, and this is going to be basic chemistry. So we go from one of the most fun lectures into one of the most complex lectures. I apologize, but that's how it goes. Now, the thing about this chemistry lecture is it's going to lay the foundation of things we'll talk about in the future. So honestly, it may seem disjointed, because I'm trying to take the most important chemical things that you'll need to know in the future and give you snippets of it rather than really going in depth. So you might have to watch this a couple times. If you don't understand something, by all means, come see me during my office hours, okay? And we're going to begin basic chemistry, okay? So I'm going to keep you zoomed in on the PowerPoints for the most part. Okay, there are a few things I'm going to have to explain. There's also different videos that we're going to watch. So I am going to put the volume up for just a second so we have it balanced, and then I'll turn off the recording. Well, it may have already stopped. Okay, because I planted some videos in here for you as well. Now, if you want to play these videos, you can absolutely do so. You just have to go in and click on the link when you have the PowerPoints filling the full screen, and you should be good to go. I have to check the video. Hold on for just a second. I'll be right back. Okay, we are definitely recording. Okay, so I'm going to zoom you in on these PowerPoints, and we will walk you through them. Okay, uh-oh. Hold on a second. I had this problem earlier. Okay, hold on. We're going to have to shoot through a couple quick things. Bear with me. There it is. Okay, so basic chemistry. Why study chemistry and anatomy? Because chemistry, at its most basic level, forms some of our physiological functions. So chemistry is important. Now, once again, a lot of you have not had chemistry for years. Some of you have just come out of chemistry. You're going to think, wow, we're going over so little. But I'm just trying to give you bits and pieces of what you need to build a foundation of physiological functions in the future. Matter occupies space and has mass, so that means that it has size. Now, mass is going to differ from weight, because weight will be how much gravity affects an object, okay? So we could have two blocks that are the same size. One is made of styrofoam, one is made of lead. Obviously, the one will be heavier because it is going to be affected by gravity. But if you put them both into an area or location that didn't have gravity, okay, their mass would be the same and nothing would be pulling them down. So mass has space or occupies space, okay, or matter occupies space. Weight is going to be how gravity affects it. Now, energy, we know, is a capacity to do work. Energy is going to give us the ability to move things. Primarily, we're talking about the energy reserves that we have in our body. Kinetic versus potential. Kinetic is going to be energy in motion, and potential is going to be when an object has a potential to move. I have a nice little video for you here. Let's watch this.
A rolling boulder crashing down the mountain. That's kinetic energy. Kinetic. A boulder sitting high upon the mountain. That's potential energy. Potential. Energy in motion is kinetic. Energy that's waiting is potential. But whether it's kinetic or potential, both of them are energy. Olay! You stretch a rubber band and then release it. That's kinetic energy. Kinetic. You stretch a rubber band and then you hold it. That's potential energy. Potential. Energy in motion is kinetic. Energy that's waiting is potential. But whether it's kinetic or potential, both of them are energy. Olay! The heat that comes when gasoline is burning, that's kinetic energy. Kinetic. The energy that gasoline is stored up, that's potential energy. Potential. Energy in motion is kinetic. Energy that's waiting is potential. But whether it's kinetic or potential, both of them are energy. Olay!
Oh, it's so silly, isn't it? But I like silly things because hopefully it'll help you to remember. Now, the thing to take away from that is obviously it's an easy definition, right? Potential is energy that is waiting, kinetic is in motion. So, where that's going to apply in the body is our storage house of energy, okay? And our storage house of energy is going to come from the foods that we eat. Instead of immediately expending them as energy, we're going to eat that foodstuffs and we're going to store them as potential energy. Then when our body needs it, can break apart chemical bonds and create kinetic energy. Okay, so kinetic versus potential. So we have chemical, which is going to be chemically bonded. Electrical is going to be the movement of ions. Now, if you don't know what an ion is, it is a charged particle, okay? It's a charged particle. There's not a ton that we're going to deal with, but I'm going to zoom out because I do want to write down on the board the ones that we are going to use. Oops, that's the wrong bar. I'm sorry. I'm having some electrical difficulties today. Speaking of electrical, okay? So, ions are going to be atoms, some of those elements that we have. One great example is going to be calcium, okay? Calcium is going to have a positive charge to it. The ones we're really going to talk about, though, are going to be sodium, okay, has a positive charge, potassium has a positive charge, and chlorine has a negative charge, okay? So these are going to be examples of ions that we will find in the body. They're atoms or elements, which we're going to talk about in a little bit, which have a charge, okay? So the movement of sodium and potassium throughout the body is going to create currents of electricity in our body, just like the electrons in lights move through the wires and conduct electricity. Okay, so forms of energy can be in our body the movement of ions or electricity per se. Okay, so mechanical energy is going to be energy in motion is actually physically moving through space. Radiant or electromagnetic is going to be like x-rays, sunlight, okay? So I'm going to zoom you back in because I have a couple pictures for you, okay? Oh, one more thing at the top there where you see chemical energy. Chemical energy, one great example in the body is going to be adenosine triphosphate. We'll talk about that several times. ATP is the short name for it, is little packets of energy that we store in our body, okay, all over our body. And the way that we make ATP is actually by using sugars and oxygen, okay? So we use sugar and oxygen to create ATP. ATP is stored throughout the body. It's that potential energy that when we need energy, our body can tap into it, okay? So moving on, I want to show you x-rays. X-rays are going to be that electromagnetic energy that we talked about. I thought it'd be fun to look at one to give you an example. Contrast studies are an example. Fluoroscopy is actually a real-time x-ray. And angiograms where a contrast is injected into a patient and they take an x-ray of the blood vessels. Here's an example of what's called a plain film. I'm going to give you a second to look at this. Now I can tell you this is a younger child. If you look at the bottom, you're looking at the pelvis, the hip bones, the femur bones, which are the thigh bones. And you can see at the top of the femur bones that the very tip, it looks like there's a round portion that's not articulated with the femur, okay? That is because that growth plate is still open. So I can tell that this is a child, a young child, okay? Probably under 5, I would guess. Now, if you look inside the bottom middle, just below where the belly button or the umbilicus would be, you can see a very white line. Now, the thing to remember on plain film is the darker the material, the whiter it will appear on the film. If I were to put a sheet of steel on a film, it would appear pure white because it would absorb all the x-rays. The more x-rays pass through, the darker the film, okay? So you can see that white line, and then just up and to the left, you see that dark area. That's actually gas, okay? So that's going to be really dark, okay, because x-rays pass right through it. But that white line is going to be, any guesses? Think in your head for a second what that might be. It's going to be metal. This child has swallowed a needle, a sewing needle, and they've taken a film that needs to be surgically removed, unfortunately, because they can perforate the bowels. And if you perforate the bowels, then feces can get into the abdominal peritoneal cavity. That's very, very bad, can cause infections. This is an X-ray, okay, radiant electricity, X-ray assisted cholecystectomy. They will use this when they are removing the gallbladder. So they can go in and have a picture of real time as to where they are and where they can guide those surgical instruments into. Energy form conversions. So energy is converted, if you remember from physics, from one form to another. Okay. One of the biggies that we'll talk about is heat being a byproduct of energy conversions from our movement. So our skeletal muscles are not very efficient in their use of their energy. And a lot of their energy is going to be turned into heat. So even though they aren't efficient, it's actually beneficial because they provide warmth, our skeletal muscles provide warmth to our body. So even though not efficient, it's really an important contributor to our existence, okay? So our muscles move, they use that ATP. Those bonds are broken in ATP of that chemical, and they are also producing heat because those chemicals are breaking apart. We'll get a little bit more into that in a little bit, so don't panic, okay? Atoms and elements, so starting at the basic. Do you remember that periodic table, okay? The periodic table of elements, there are about 112 known for sure. I think it's actually up to 120 now, but 120-ish. Okay, 92 occur in nature, some are artificially made. What we're really going to work with is just several that'll repeat over and over. So don't think that we're going to be going back to that periodic table and studying all those elements. That's not our goal. Our goal is to focus on probably 7 of them, okay? And we can see 96% of the body weight is carbon, oxygen, hydrogen, and nitrogen. Okay, 20 others in trace amounts. We're going to focus on sodium, potassium, calcium, okay? So anyway, those elements, they have a symbol, and then they have numbers affiliated with them, telling approximately how many protons or electrons they have in their formation. Now, we'll go over that study in a little bit. I'm getting ahead of myself, okay? So atoms. elements in the body, some that are important. Don't worry about going through and memorizing these at this point. What I would like to do is introduce them to you as we find them important. Okay, so when we start to talk about water and where water goes in the body, we'll talk about sodium. And where sodium goes, water goes. That's a big one. Okay, calcium we're going to study when we study the bones, etc. But just to give you a template about the ones that are going to be important. All about an atom. Remember the picture of the atoms? If we go, here we go. Okay, in the center we've got those protons and neutrons, and then on those orbits around the outside there's electrons. So we're all pretty familiar with that. The protons are positive, the neutrons are neutral, and electrons are negatively charged particles. Okay. So those protons and neutrons are in the center. Those electrons are going to be orbiting around the outside. Now, these atoms will combine together to form molecules. Okay, you can have molecules of the same atom, or you can have compounds, which are going to be two or more different atoms compounding together. You don't really need to know the difference. You just need to understand that atoms are going to bond together in different ways. We're going to talk about how they bond in just a couple of slides. Okay, so these atoms will combine together or bond together to form molecules. So let's look at a quick little video about making molecules.
This tiny drop of water is really made of millions of tiny molecules, and those millions of molecules are made up of tiny atoms. Ha! Can you believe it? Amazing! It all starts with the atom. In their natural state, an electrically neutral atom has the same number of negatively charged electrons as it has positively charged protons. The protons are found in the nucleus, and the electrons are located around the nucleus. The electrons are distributed in shells. The first shell can hold 2 electrons, the second can hold 8, and the third can hold 18. The electrons in the most outer shell of a particular atom are called its valence electrons. Atoms react chemically and bond with other atoms with these valence electrons. Atoms are real control freaks. They're always trying to fill their shells. If an atom has 1 electron in its second shell, it will try to lose 1 electron or gain 7. And let me tell you, it is much easier to lose 1. With more than 3 valence electrons, it's easier to get electrons by sharing them with other atoms. Let's look at hydrogen. It's in the first group of the periodic table. It only has 1 electron in its outer shell, just like all the other elements in the same group, because elements in the same group have similar chemical and physical properties. All of these elements bond very easily with other elements that like to gain 1 electron. Hydrogen is a bit unusual, since it only needs 1 electron, not 7, to fill its shell. Hydrogen is happy to share an electron with another atom to fill its shell. Take our drop of water, for example. 1 water molecule is made up of 2 hydrogen atoms and 1 oxygen atom. The oxygen atom has 6 electrons in its outer shell, or a valence number of 6. It would love to gain 2 electrons. Each hydrogen atom has a valence number of 1. And when the 3 of them get together, they really bond. Behold, the water molecule.
Okay, that is, once again, I know that this is a basic review for a lot of you, but it's a great little video if you need to review these and you have done chemistry for a while. Okay, so basic structure of an atom we went over. Those electrons, how they interact with other ones. So let's talk a little bit more about that, and we're kind of going to review that tape. So there's a planetary model versus an orbital model. I don't care if you know the difference. It used to be said that the electrons go through orbits, just like the orbits of planets around the sun, but now they have a whole area, which would be the example on the right, that they can move through. Whichever way you want to think of it is fine. I would never ask you about that on an examination. Okay. So different atoms are going to have different numbers of protons, neutrons, and electrons. They're going to have the same number of protons and electrons if you're just talking about the atom by itself. Okay. The atomic number will be the number of the protons in the nucleus. And as that atom's by itself, that will have the same number of electrons, okay? It's written by a small number to the lower left. A mass number is going to be the number of protons and neutrons in the center of the atom, okay? It's written on the high left. Now, an atom can actually have different numbers of neutrons in the nucleus. That's where we get isotopes. You've probably heard of different isotopes of carbon. That's one of the most well-known isotopes. That means that there are different numbers of neutrons in the center of that atom. They can be unstable, and they could turn into what are called radioisotopes, which are radioactive, okay? So atomic weight is going to be the average weight of all those isotopes. So if you look, there's all different types of isotopes of carbon. In order to get the atomic weight of carbon, they average the weight of all those different carbons together. I am not going to ask you about that on an examination, by the way, okay? I mostly want you to know the atomic number and how it relates to the number of protons and electrons in that atom, okay? Here is a brief little video.
Hello and welcome to another Science Revision video. Now in this video we're looking at atomic number, mass number, what we call isotopes. So let's begin, shall we? Let's look first of all at atomic mass and mass number. Now every element, all 110 or whatever, how many there are, have got two numbers attached to them. This is the symbol first of all. Now this is a symbol for sodium. It's a bit odd, isn't it? You thought it might be SO or something. No, this is Na. The symbol for sodium is Na. Now there are always two numbers attached to these. There's a big one, like this one, 23 here, and 11 here. Now what are they? Well, first of all, the 23 is a mass number. Okay, a mass number. And this tells us the total number of protons and neutrons. Down here we've got the atomic number. And this is a number of protons. It also tells us how many electrons there are as well, which will come to in a second. Now most textbooks, most periodic tables have them this way around. In a few textbooks and a few periodic tables, for some reason unknown to me, they actually put these the other way around, which is a little bit confusing, isn't it? Make sure though you always remember this one is the big one's a mass number or an atomic number. Now we can work out the number of neutrons by subtracting these two figures here. You want to work out how many neutrons there are in sodium, you subtract 11 and 23. So, oh, forgot about this bit.
Okay, that's getting beyond what we need to do. I basically wanted to do that so you could see a picture of how that atomic number and mass number look. Okay, so you've got the symbol, you've got that atomic number and that mass number. That's as far as we're going to go with that. I also just like that tape because I like his accent. I think it's pretty cool. Okay, so how matter is combined. So this is going to be molecules and mixtures. Okay. Great song. I'll play it at the end so that way if you don't want to listen to it, but it's just fun. Once again, child of the 80s and the 90s, They Might Be Giants for those of you who were born in the same era as I. So molecule is going to be two or more atoms, okay? Can be the same atom joined together, okay? It can be a molecule of different atoms. So it could be a molecule of the same element or a molecule of a compound. It's going to be different atoms. Very different characteristics, okay? Sodium chloride makes salt. When you're talking about sodium and when you're talking about chlorine separately, very different characteristics from table salt. Okay, so molecules and compounds. Different mixtures. So this is when different components are mixed. So this is what you really need to think about when we're looking at this, is what is a solution? A solution consists of a solvent and solutes. I'm going to bring you back out, hopefully to the right screen. Okay, sorry, there we go. Okay, so we're talking about a solution here. So on the screen, I want you to understand the other concepts, but the real take-home message is a solution and that it's comprised of a solvent and a solute. Okay, so here's a solution. A solution is comprised of a solvent and a solute. The solute is dissolved in the solvent. The way I always remembered it, because I always had a problem, is water is the universal solvent. And water, that W, I don't know, for some reason the V from solvent reminded me that it looked pointy and sharp like the W from water. I don't know if that helps you or not. Okay, so water is the universal solvent, and water is going to be the solvent. There's all different types of solvents. The only solvent that we're going to talk about is water. Water is going to be the solvent of the body and has very specific chemical properties as to why it is a very good solvent for us. But if we're just talking about a solution, we're talking about salt water. The solvent would be water, the solute would be salt. Okay? Okay? So if we're talking about, salt water in the body, it's going to be salt is the solute, water is the solvent. So, okay, so that's a general gist of that. Now, I'll go on under that mixtures and talk about colloids. Okay, they're milkier and they can change from a liquid to a gel or a solid to a liquid. Okay, they look milkier because the solute is bigger. Okay, and suspensions where the solute can settle out of the solution. This is an important concept when we talk about blood, because when we examine blood in a chemical or a lab setting, we extract the blood, okay, we test it for different substances, but we can spin it out so we can let red blood cells settle out of that solution. That's because blood is a suspension, okay? So I'm going to zoom you in. I'm going to close the window because you might not be able to hear me. Hold on just a second. Okay, this should be better, I hope. Okay, mixtures, unlike compounds, have the following characteristics. There are no chemical bonds. They can be separated and they can be homogeneous or heterogeneous. Okay, now, so the first two are pretty self-explanatory. Homogeneous means that they can be the same throughout the whole mixture, that the solute is spread evenly throughout the solution, or they could be heterogeneous where they can be separated into areas where we have more concentration of solute. Okay, so mixtures. Chemical bonds. So we talked about the atoms, we talked about the basic structure. Now we're going to look at how they can bond together. Okay, we looked at the electrons in that chemical bonding and we know that they fill those orbits. Now, I go through the different levels and how many electrons can fill them. You could go up to 7 shells, okay? The only 2 levels that we will deal with is the first one can fill with 2 electrons. The next one can fill with 8. That's about as far as we're going to go. Now, what I do want to point out to you, though, oh yeah, I got it right. Okay, what I do want to point out to you is the valence shell, or the outermost shell. It actually participates, I think it's on the next, yeah, it's a little bit further ahead, but anyway, we'll talk about the outermost shell is going to be the shell that interacts with other electrons. So if you have, on the next page, if we look at those examples, okay, if you have carbon as an example, carbon is going to have 6 protons, so therefore it will have 6 electrons. So you could see from the next picture that carbon, okay, will have 6 electrons. So it fills its bottom shell first. They always fill the bottom shell first with 2. And then it will start to fill the outer shell with 4. So now you have 6 electrons. This fellow's lonely. He wants to have at least 8 electrons in his outer shell. So he'll be looking for how many? 4. Okay. So a lot of times carbon will bond at the 4 corners with another atom, or 4 other atoms, I should say, to make it stable. By filling these shells consecutively, 2 on the innermost, 8, then 18, etc., up to those 7 levels, it makes the atom stable. Otherwise, that atom's looking for a date. It's looking for an electron to fill its shell. Sounded bad, sorry, but I didn't mean it that way. Okay, it's looking for electrons to fill those shells and make it stable. Okay, so let's see. Okay, good. Moving on. Now, noble gases. Okay, noble gases are chemically inert or non-reactive. The outermost energy level is full. So it can be full with 8, but we can also have 2, okay? Helium is an example. They don't like to share. They're good. They're on the far right of the periodic table. There's helium. Helium has 2. He's good. He is full. He doesn't need anything else. Neon is going to have 10. You could see 2 on the innermost and 8 on the outermost. Okay. So that valence shell is going to be that outermost energy level that will interact with other atoms we talked about until it is stable. It follows what is called the octet rule, creating full outer shells to make it stable. Okay. So ionic and covalent bonding is how we do this. Let me show you a little animation and then we'll go through the rest of the notes about this.
Ionic bonding occurs between 2 atoms when one of the atoms has sufficient strength of attraction to remove an electron from the other atom. A sodium atom has 1 valence electron, with a stable energy level below containing 8 electrons. A chlorine atom has 7 valence electrons. If the atoms collide with sufficient energy, the chlorine atom will remove the electron from the sodium. The sodium atom loses its only valence electron and becomes a positively charged sodium ion. The energy level below now provides sodium with its stable octet. The extra electron completes a stable octet for chlorine, which becomes a negatively charged chloride ion. Covalent bonding occurs when neither atom has sufficient strength to completely remove the other atom's electrons. The atoms share electrons, and both atoms achieve a stable outer energy level. A hydrogen atom with 1 valence electron needs 1 additional electron to complete the first energy level. An oxygen atom has 6 valence electrons and needs 2 additional electrons to complete the second energy level. As the oxygen and hydrogen atoms collide, covalent bonding is accomplished by the sharing of electrons. By sharing an electron pair with the oxygen, the hydrogen completes the noble gas configuration of helium. By sharing with a hydrogen atom, the oxygen atom now has 7 electrons in its energy level, still 1 short of the stable octet condition. A stable octet for oxygen can be completed by sharing an electron with another hydrogen atom.
Okay, so that's a great little animation about how you can have 2 forms of bonding, ionic and covalent. So let's go through that again. So ionic is when atoms lose or gain electrons. Now don't forget, electrons are negatively charged. So if you lose an electron from an atom, now that atom is going to have a positive charge because it has more protons than it does electrons. Once again, I know this is review for many of you. So, you know, just let it sink in. And for people who need the review, okay, or help with this, let me know. So anyway, so atoms lose or gain electrons. If they lose an electron, they're going to have a positive charge. If they gain an electron, they will now have a negative charge. Now, they showed you an example of sodium and chlorine. Okay, sodium loses an electron and chlorine gains it. Now, because the sodium has a positive charge and the chlorine has a negative charge, they actually are attracted to each other because opposites attract, and those positives and negatives attract to each other. Ionic bonds are usually going to form salts or crystals. Perfect example, sodium chloride. Okay, covalent bonds are going to be shared electrons like we saw with the water. okay? Maybe shared with one or more, there may be multiple, there may be a whole bunch if you've studied organic chemistry, okay? Hydrogen bonds are kind of special bonds. It's when hydrogen and oxygen, so two hydrogen and one oxygen join together. And the thing about the hydrogen bonds is even though they form a covalent bond, there is a slight charge across that molecule, making it what's called polar. Now, this is very important because there is a slight charge across water molecules. It makes them really good at carrying ions. So come back out with me for a second, okay? Because oxygen is a huge hunk and atom compared to the hydrogens, it tends to attract the electrons a little bit stronger than the hydrogen. So when we're looking at oxygen and our little hydrogen molecules here, okay, oxygen is bigger, hydrogen is smaller. So the oxygen side tends to have more of a negative charge to it. This is great because this will take different ions and spread them evenly throughout the that universal solvent of water in our body. So if we pour some salt into our system, it doesn't all clump into one area. We'll break that salt apart into sodium and chlorine, and that sodium being positively charged will latch on or be attracted to that negative side of the water molecule. The chlorine being negatively charged will be attracted to the positive side, and you get an even distribution of sodium and chlorine throughout the blood, okay, and throughout the tissues. So this polar aspect of hydrogen bonds is very important in order to distribute ions throughout the body. Let me show you the video.
The atoms that make up a water molecule are in a constant tug-of-war over their shared electrons. Oxygen exerts a far stronger pull on the shared electrons than does hydrogen, and so the electrons spend more of their time closer to the oxygen atom. Because of this unequal sharing of electrons, the oxygen atom in a water molecule actually has a slight negative charge, and each hydrogen atom has a slight positive charge, even though the water molecule as a whole is neutral. Because of the unequal sharing of electrons and the resulting positive and negative poles, a water molecule is said to be polar. The polarity of water molecules causes them to be attracted to each other. Since the positively charged atom involved in this special type of attraction is always a hydrogen atom, this kind of bond between molecules is called a hydrogen bond. Each water molecule can hydrogen bond to 4 other water molecules. A hydrogen bond is weak and lasts only a tiny fraction of a second, but it takes a lot of energy to overcome the combined attraction of many hydrogen bonds. This explains water's great capacity heat, its high boiling point, surface tension, and several other unusual properties.
Okay. Okay, so types of chemical bonds. So ionic, covalent, and hydrogen. Okay. Here we can see those sodium and chlorine atoms and how they're, because they have transferred that electron, they are attracted to each other because of their opposite charges. Okay. There's another visual of that. Now, here's a covalent bond. Remember I talked about carbon. Okay, carbon's really essential, especially in organic chemistry, because it has those 6 electrons in the shells. It likes to attract 4 atoms to make it stable. This is actually a methane molecule, okay? And it becomes the core of many of the long chains of carbon that are essential to build carbohydrates and lipids and proteins, okay? Well, I should say carbohydrates and lipids. Okay. Here's that V shape of water with a negative and the positive charge. Okay, sorry about this. Let me just, sorry, it's really loud. I don't know how to stop it from doing that. But I mean, anyway, chemical reactions or chemical bonding. So temperature, okay, if we increase the temperature, we increase the interaction of cells because we create more movement in that solution. Okay, so you create more movement, those cells bang, bang, bang more together. See Same thing with the concentration. If you increase concentration, you're going to increase the chances of chemicals meeting each other. Particle size of molecules. The smaller the particle size, the more there's interaction. It increases the surface area. They're able to move quicker and they can interact. So that's kind of counterintuitive. Smaller particle size, the more interaction. Catalysts are equivalent to enzymes. If you add a catalyst or an enzyme, you'll facilitate or increase reactions. Okay? So an enzyme basically is a little helper that comes along and puts chemicals closer together, helps them interact, and then it releases and it goes away. Chemical equations. So there are different types of chemical equations. This looks complex. It's really simple if you think about it for a second. A synthesis reaction is when you add two substances together. A plus B equals AB, okay? Also known as endergonic. It takes in heat, and anabolic because it builds up. Anabolic is another word for metabolic reactions that build tissues up or put them together. If I were to go out today and pump up on some anabolic steroids, I'd be a big person. Anabolism is a metabolic process where you build things up. Decomposition reaction is when you break them apart. It's exergonic, it gives off heat. It's also known as catabolic or breaking things down. Catabolism is breaking things down, okay? Can be reversible. If it's reversible, it's indicated by double arrows, one going one way, one going the other way. I'll exemplify that when we need to know it, okay? Can you have exchange reactions where if we put A and B plus C, it can change into A and C plus B, okay? So the definitions are exactly what happens in those chemical reactions. Don't make it any more than it is, okay? Synthesis reaction, an example. Amino acids are the building blocks of proteins. They are small chemical structures that we link together, and when we get 20 or more of them, I believe is the number, it's considered a protein, okay? It may be smaller than that. I'm sorry, I kind of forgot. If anybody knows, let me know. So we link those amino acids together, we create a protein, okay? Decomposition reactions. Glycogen is the stored form of glucose. Make note of that. We'll talk about it several times. Glycogen is the stored form of glucose. So when we go out and we eat something that has glucose in it, our body will break down that foodstuffs, absorb the glucose from it, then link it together as glycogen, okay, if we don't use it initially as energy. So glycogen is the stored form of glucose. That's the end of the lecture. Wow, it took me by surprise, okay? Chemistry is tough for people who haven't had it before. Watch this tape a couple of times, review in your book. If you need my help, I'd be more than happy to help you. For those of you who consider it a review, I totally understand. Zip through the lecture once and it should make sense for you. Next video is going to be about biochemistry. It's going to be the chemistry of the body, the basic chemistry of the body. I thank you so much. Please email me if you have any questions. Thanks. Have a great week.